Another important concept and definition is isotopes. Isotopes are defined as atoms of the same element, but with a different number of neutrons. If you look over here, as I circled, the number of protons does not change for carbon. However, the number at the top, which is the mass number, is changing. And the reason why it's changing is because you have more neutrons. You can tell from these images, pictures, that the number of neutrons is increasing. So if you count how many neutrons you have in this one, you have 6. If you count how many you have an additional 1, you have 7. And in the third one, you have 8. So number of protons in the first one is 6. The number of neutrons is, remember, 12 minus 6, which is 6. In the second one, the number of protons is 6. The number of neutrons is 13 minus 6, which is 7 now. So notice that the number is changing. And then in the third one, you have 6. But the number of neutrons is now 14 minus 6, which is 8. So once again, the number of neutrons is changing in these. So these are isotopes of each other. And every element has isotopes. In fact, the carbon in your body, it has also these isotopes of carbon. Of course, some are major, or they're available or present in bigger amounts, in much bigger amounts, like carbon-12. The majority of carbon in your body is carbon-12. But there's a little bit of carbon-13, almost none of carbon-14. There's one thing that we would like to learn here is that when we write the number of, or when we write the isotope name, we always write the element's name. So in this case, we say carbon, and we always follow that by the mass number. So it goes like this: the element's name, and then the mass number. And the reason why you do this is because, once again, the number of protons, or the atomic number, does not change. So that is why we don't include it, because all carbons have 6 protons. However, not all carbons have 6 neutrons. So this one right here, again, refers to this one. So if we want to write the formula for the second one, we would write carbon 13. Again, this is this one right here. Now you will see when we get to the periodic table, and after this, we will stop writing this number down there because, again, this number does not change, and you can look it up very easily from the periodic table. So let's do another one. Here's another interesting application that you're going to like. And this is about the use of iodine. And iodine can be used for imaging. Also, it could be used as a radioactive element to treat cancer in the thyroid cancer, especially iodine-131. So if you notice here that the thyroids in the body are actually emitting radiation, and if there is suspected, let's say, a cancer in the cells, what would happen is that these radioactive iodine atoms are actually absorbed by the thyroid and most types of thyroid cancer. So what happens is that these radioactive iodine atoms, they build up in the thyroid tissue, and then they use some kind of what they call a gamma camera that actually detects these radioactive emissions. And what you see right there is this is the emission right here. Okay, so let's do these and see what is changing. So if we do the number of protons, the number of electrons, and the number of neutrons. So the number of protons in here is 53, has not changed there again. The number of electrons also is 53. It is also 53. And then the number of neutrons is 123 minus 53, which is 70. So you have 70 neutrons in the first one here. And of course, in the second one, you have 131 minus 53. It's a number on the top. And that would give you 78 neutrons. So this one is heavier. Now you might be asking, a last question is, how do I know when the electrons are going to change? We will examine this when we get to ions, where actually you will see a charge on the top on the upper right-hand corner. And you will have either a positive or a negative, could be followed by a number. And then you will use that to determine how many electrons you have, whether you have less than the protons or more than the protons.